Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Deep within the murky, silt-heavy waters of the African and South American river basins, evolution has spent millions of years perfecting a sensory system that makes our five senses look primitive. While humans rely on light and sound to perceive the world, certain species of weakly electric fish, such as the Peter's elephant nosefish, navigate a world of pure energy. They possess what scientists call an active sense, the ability to generate their own electricity and perceive how their surroundings distort that field. This isn't just a biological curiosity. Today, this ancient evolutionary hack is providing the blueprint for a revolutionary leap in robotics, the development of the voltammetric tongue. To understand why this matters, we first have to look at the challenges of underwater exploration. For decades, roboticists have struggled to create autonomous underwater vehicles, or AUVs, that can navigate effectively in turbid water. In environments where visibility is near zero, traditional cameras and even high-frequency sonar can fail. Lasers get scattered by particles, and sound waves can bounce off chaotic surfaces, creating a mess of data. This is where the electric fish comes in. These fish create a weak electric organ discharge, establishing a dipole field around their bodies. As they swim, any object with a different conductivity than the water, be it a predator, a piece of prey, or a plant, will distort that field. By sensing these minute perturbations through thousands of electroreceptors on their skin, the fish creates a high-resolution, 3D map of its environment, regardless of how dark or muddy the water is. But the innovation doesn't stop at navigation. Researchers have discovered that these fish aren't just seeing with electricity, they are effectively tasting the water's chemistry. This is the concept of voltammetry. In a laboratory setting, voltammetry is a technique where scientists apply a varying voltage to an electrode and measure the resulting current. This allows them to identify specific chemicals based on how they gain or lose electrons at certain voltage levels. For an electric fish, the varying impedance of the water acts as a natural laboratory. They can detect changes in salinity, the presence of heavy metals, and even the pH of their environment by analyzing the feedback from their own electric pulses. Engineers at leading tech institutes are now translating this biological process into hardware. The result is the voltammetric tongue, a sophisticated sensor array for robots that mimics the electroreceptive skin of the fish. By integrating these sensors onto the hull of an underwater drone, researchers can create a machine that tastes the water as it swims. Unlike traditional chemical sensors, which often require physical samples to be trapped and analyzed over several minutes, the voltammetric tongue works in real time. It can scan for specific molecular signatures, such as lead, arsenic, or industrial runoff, as the robot glides through a river or a port. This technology is a game-changer for environmental monitoring. Imagine a swarm of small, biomimetic robots released into a lake after a suspected chemical spill. Using their voltammetric tongues, these robots could instantly map the concentration of the pollutant, following the chemical trail back to its source like a bloodhound. Because the sensors are based on electrical impedance rather than delicate optical lenses, they are incredibly durable. They don't get blinded by mud and they aren't as prone to biofouling, the buildup of algae and organisms that typically ruins underwater equipment. Furthermore, the integration of artificial intelligence is taking this to the next level. By training machine learning algorithms on the electrical signatures of various chemicals, these robots can now distinguish between harmless minerals and dangerous toxins with incredible precision. The robot's brain learns to interpret the complex waveforms of the electric field just as the fish's brain does. We are effectively teaching machines to perceive a hidden dimension of the physical world. As we look to the future, the applications of the voltammetric tongue extend even further. From monitoring the health of coral reefs to checking the integrity of deep-sea oil pipelines, the ability to sense water chemistry through electricity offers a window into environments that were previously inaccessible. It is a perfect example of how looking backward at millions of years of biological evolution can propel our technology forward into the next century. The humble electric fish, once a mystery of the Amazon and Nile, is now the primary instructor for the next generation of environmental guardians. By bridging the gap between biology and electrochemistry, we are finally learning to see and taste the world through the eyes of the living circuit. For more incredible facts like this, don't forget to subscribe and turn on notifications.